Okay, thank you for your kind patience. So, let's start from what is the actual definition of multi-objective optimization, what we are optimizing, and what is the, let us understand what is the exact decision space and objective spaces. So, I need your kind attention in this slide. Suppose we have a vector like this. Here we have x1, x2, xn. These are the function inputs. As we have seen earlier, suppose we have xy. So those x and y are these x1, x2, xn. Okay. Suppose we have a set of objective functions f1, f2 up to fk. So this is the vector containing the values of the individual objective functions, and these are some inequality constraints, and these are some equality constraints. So this is the problem statement for multi-objective optimization. So what is the difference between single objective and multi-objective? This particular vector, right? In case of multi-objective optimization, we have more than one values in objective vector. Can you please tell me, is there any problem in this slide? Transpose, actually it is transposed for computational issues. I mean, this is a row vector basically. It is transposed when it gets in the column form. So it is transposed due to the computational purposes, nothing else. You can ignore this transpose, okay, for the time being. So let's see. In this case, what we are doing, suppose we have a value of x like our normal function, and we have a particular function y, right, y equal to fx. So we have plotted it, right, in the y direction we have plotted y value, in x direction we have plotted the value of x. That's it. And in this case, what we are doing, we are plotting the same thing but for different functions. We have multiple functions, right? Now this is an example of a single objective function where we are trying to maximize z1 depending on this function, where x1, x2 are the decision variables. Right? This is an example. Now we have an elaborative example. This example will help you to understand about the decision space as well as objective space. We have two decision variables, x1 and x2, and we have two objective outcome, or maybe you can say we have z1 and z2 as two different objectives, right? Two outcome of two different functions. Okay. So we have plotted the values of x1 and x2. I am elaborating this plot. See, the point A is 0, 0. Dot is slightly shifted, and I beg your pardon for that. In B, we have 0 and 3.5. Right? In this way, we have plotted it. This particular plot is showing you the decision space. What does it mean? The possible solutions from which we are searching the objective. Right? We are trying to minimizing or maximizing the objective.
So that has coordinates x and these are x1 and x2.
Yeah, x1 and x2. We have two variables, x1 and x2. If we have single variable, then it will be a straight line. On that particular line, we can plot it.
And this does not show the values of the J1 and J2 for each of these variables?
No, in decision variable space, we are just dealing with the decision variables. That is the input to that function. Objective function values will be plotted to the objective space. Let me show you. This is the objective space where we are plotting Z1 and Z2. Right? How we are getting these values? We are getting these values by applying some function. We are using a single function for Z1 and we are using another function for Z2.
So here the coordinates are Z1 and Z2.
Yeah, Z1 and Z2. Right? So what we are doing, we are giving some input to these two functions. These two functions producing some values. We are plotting those values. Okay? Now, what is our ultimate goal? In case of single objective problems, we have a single function, for example Z1 only, and we are trying to find minimum or maximum from this particular function. Right? In this case, it may happen that we are trying to maximizing Z1 and minimizing Z2. Alright? So, in this case, the objectives may be conflicting.
So in the Z1 Z2 space, there is no notion of maximizing minimizing because both are equally important. F1 and Z1 Z2 both are equally important.
Equally important. If you put some weights like our
If you put some weight,
yeah.
it will become a constraint.
Yeah, then it will be a single objective problem. In this case,
So it will not be a Z1 Z2 case then.
no. If we multiply it with some weights, then it will be not a Z1, Z2 case, it will be converted to a single objective problem. That is why I have said earlier that our objective is to optimize both of them. But how can it possible? I am coming to that point. So just visualize side by side what is the decision variable space and what is the objective space. Right? So what we are doing, we are converting the decision space. We are taking some value from decision space and we are converting it to the objective space. In this diagram, we have three decision variables x1, x2, x3, and we are converting it to the objective space where we have f1 and f2, two objective functions. Okay. So, can you please tell me what are we searching for? Yeah, that is our goal. We are trying to, for example, in case of single objective functions, leave it multi-objective problem. Suppose we are trying to purchase apple in a single objective manner. So what we are trying to do, we are trying to get better quality apples, right? That is our objective. But what we are getting, are we getting quality or price? We are getting apples, right? Are you getting my point? So what is my point in this case? We are using these values to compute the objective space. We are trying to optimize in objective space, but our ultimate goal is to search these values for which that optimal value can be achieved. Please, I want to make this point very clear. Is it clear to all of you? We are trying to search these values, these decision values, for which objectives are optimized. So our ultimate program or function, whatever you may call it, that will return the one second, sir. That will return x1, x2, x3 for which f1 and f2 are optimized. Okay, please, sir.
So our goal is the f1, f2 plot only. Our ultimate goal is to look at the f1, f2 situation.
No, our ultimate goal is to optimize those functions for which these x1, x2 and x3 values.
For which decision variable we are getting the.
Yeah, we want to get the decision variables. We are not wanted to get the optimal result. We want to get the decision variables for which those optimal results can be achieved.
Yes. Optimal results can be observed on the decision on the objective space.
Yeah.
And so there are some. So if we look at the if we can maximize, if we put our interest to have a maximum value of f1, or if we put our interest to put the maximum value of f2. So there is two boundaries that we can set on this region that we have.
Yeah, if we actually I am showing you that I have not discussed yet. Whenever you are trying to optimize these two functions parallelly, what may be the outcome? Okay. For single objective, I guess all of you have an idea. whatever I have discussed till now, that for a particular objective function, we are trying to maximize it or minimize it, and for which decision variables we are getting that particular optimal value, that is of our interest. Okay, in case of multi-objective optimization, what will we get? I am coming to that point.
So is it a one-to-one or one-to-many mapping? So what is the
Which one?
for each division space we have separate like unique solution in the objective space, or it can be
Not necessarily unique solution. You can get similar kind of solutions for two decision variables. Often happen.
Okay, so is it possible like for a single division variable we can get multiple objective functions
Multiple
like objective
values?
Yes.
No.
Is it
For a particular function, if the function body is defined, how can you get more than one value for a single thing?
like one to the
No, on means from there that side can be
Yeah.
one, this side can be one. No.
No, actually objective value is can be multiple, but
Yeah, for different decision values, objective values can be single or multiple. But for a particular decision variable or the set of decision values, we cannot get multiple objective values. For the different objective functions, you will get a single values for each of them.
that means all solutions should be disturbed in the division space because like
All solutions?
should be disturbed in the division space like we
Yeah, we have to return the value of the decision variables at last.
that means the domain is division space, right?
Search domain, definitely. This is decision space is also called as search domain.
No, the
Domain of
function
search.
domain,
Sorry?
actually. The function domain.
Function domain, yeah. That actually these functions are taking value from these domain
The
only.
any variable like any variable should be exist so that the division space don't have that particular division value. So that,
Sorry.
Like in the objective space,
No.
is it
Is it not possible? How can it be possible? Because if anything is existing, suppose you are talking about like this. For example, suppose we have an apple that is not existing, but the fruit seller has put a price tag for that invisible apple.
Sir, I think that this is a one-to-one.
One-to-one.
One-to-one. Exactly. The reason is
Yeah.
for any point x1, x2, x3, we will get a specific value of f1 and f2. That will equalize to only single point compare f1 and f2. Clear?
This one, right?
Yes. One.
See, it depends on the function type you are defining. In this case, maybe f1 and f2 gives you a single value, maybe. But in many cases, it happens that for a particular value, you can get similar objective
If the
outcome.
link between the non-linear, then it is a possible value.
Yeah, for example, suppose two apples quality are there, you are getting the same price, like that. Am I clear to all of you? It is often possible for two values in the decision space, we may get the same objective outcome.
No, for two values, see, here you are getting. So, can you tell again what was
What I am trying to say that suppose we have a set of values x1, x2 and x3. We have another set of values x1, x2 and x3.
like price, weight, those
Maybe.
those.
No, those are the price weights are the objectives. In that example, apples are your decision space. We are trying to optimize prices, weights and so
How do you
on.
specify an apple?
By a number,
By
you can put a number in program.
No, by an apple.
No, he's talking about the features of that.
Yeah, features.
When an apple is specified by its price, its weight, or some other parameters. That is,
Yeah.
So more parameter you put, more x1, x2 will generate. So it will be x1, x2, x3, x4 like that.
I got your confusion. Actually, in that apple example, you are thinking that price is a decision variable.
Okay, I forget price. Then say you take other parameters. Like weight is one parameter.
Yeah.
Weight is another one parameter. Say, other
Case cannot measure. Okay. Maybe. Weight is a parameter definitely.
So see, several such parameters. So leave the price. I think because you are attaching price to the objective to it.
Yeah.
Attaching price to the objective. So that is one f1.
One f1.
Another f1 will be something else.
That can be your weight. If you are trying to optimize your weight, that can be another objective function. Not necessarily you have to quantify those apples using some numerical value. You can put just 1, 2, 3, 4 numbers to the apple. When you are coding it, you are just put 1, 2, 3, 4 numbers and you are getting those values from the market. Then you try to optimize it. I think I'm not clear to you.
No, actually, what I have understood, what he meant to say that if you are purchasing Apple on the basis of 3 features, so you will be having 3 different functions. Finally, you will be calculating 3 different functions which will be based on those 3 different variables. That is what finally it is going to return. That's why he has written the f1 of
So even if you are saying that the features itself are function,
features are variables. Features are variables which will be put into different types of functions.
No, one, I guess the confusion is raising due to the understanding of quantifying a value or quantifying a particular thing with its objectives. So, actually, I got your confusion, but in case of apple example, I think you should consider those apples as numbers. I mean, you can say first apple, second apple, third apple, and so on. When you are trying to optimize something, for example, if you are trying to get the highest weight, you are trying to get the lowest cost, you are trying to get the highest firmness, those are objectives. You are trying to optimizing those objectives.
Now, if we go back to the earlier slides,
কোন slide?
আগের স্লাইডটাই যেখানে ইনিশিয়াল যে ফাংশনটা কেমন হবে দেখতে লেখা পরে আসবে যেখানে ফাইনালি ম্যাথমেটিক্যাল ইফ ইউ কাম হিয়ার যে আমার যতগুলো উপরে ভ্যারিয়েবলস ছিল সেই নাম্বার অফ কি আমার ফাংশনস থাকছে
না, not necessarily. Number of decision variables and number of functions are completely independent.
So what are those x1, x2 for the apple case? If you can mention one of those, you can trace.
Yeah, I got your point. Actually, that is what I am saying. In case of apple case, when you are trying to code it,
We are not able to put x1, x2.
yeah, no. When you are trying to put it, I mean, when you are trying to
So
what can I say?
x1 is not an apple. x1 is a feature of an apple.
Yeah, x1 and x2, all these things are input to that function depending on which we are computing the objective values. Now, tell me, when you are getting the price of the apple, how can you get the price? Is there any function involved? It is directly getting from the seller, isn't it? For that apple example, it is very difficult to define that function itself because price is getting from the seller, the firmness is getting by your sense.
So if you follow the idea of putting the price itself in the objective itself, so that see the price tag with the apple and the price that you are paying, those are two different things, na? So the price tag with the apple is a feature of the apple.
Price tag of the apple.
Price tag of the apple is a feature of the apple. But the price that you are paying for buying those many apples, that is an objective.
No. In that particular, I'm sorry, but actually I maybe confused you. In that particular example, that's a very simple example. I am expecting that the price tag on the apple is the final price of that apple. You have to pay. You cannot bargain
You
there.
are not buying a single apple. You are buying a maybe.
Whatever may be there, that is in kgs. So suppose 150 rupees kg, you have to pay that. If there is no chance of bargaining, you have to optimize that value.
You are both maybe buying a say you are a shopkeeper. So I am a shopkeeper. I am getting the apples from the wholesaler. So I will be buying say 2 kgs of that, 3 kgs of this, 5 kgs of those. All together I put in my showcase all those for selling.
Yeah.
So that situation is right. Could you explain that? So the objective function is about buying many apples, many different prices.
See, in that particular case, our objective was not to buy many apples. We have to try it to identify the apples which gives you the best value for money, if you can remember. In that particular case, we have converted the whole thing into a single objective and we have identified the best value for money.
That is the oversimplification.
Yeah, oversimplification. I have earlier said that for the beginning, I am taking a very named example. And for that particular case, I can clarify it further. I can understand your confusion. See, for the Apple case, suppose we have a database where we have the prices and weights are stored. For example, this is price, this is weight, this is firmness, quality, and so on, right? Those things you are considering as features, right? But those are not features. You are trying to optimize those values. For example, price is 100, weight is 50 maybe, and firmness, suppose it is identified by some ranks 0, 1, 2, etc. Right? Suppose we have a function. We have a function f. We are giving 1, right? We are giving 1 inside it, and this particular function is fetching these values from a particular database. Are you getting my point? We have a function. Inside that function, we are giving value 1, and that indicates the apple number 1. Right? In this case, this x1, x2, there is no more than one decision variable. It's only one variable apple.
Now, there is a constant, there is a uniqueness constant here. Because I may have another type which is exactly mapping those terms.
Not an issue. Because if you have, suppose 252, not an issue. When you are fetching those values in objective domain, objective space, suppose we are giving 2 here, it will return the same number of values. You are getting the same objective values. These values, I mean, whenever you are putting 2 in a particular function, it will return you a vector, right? Containing this set of values. Those values are individually being optimized. Your optimization algorithm will optimize individual values of that particular vector.
Solution to the problem may be two different.
Yeah. 2 or 3 or 4, that is called the parallel front. I am coming to that point. There may be more than one solution. But can I consider that the confusion is clear? You are just confusing with that particular vector and maybe the f1x and f2x. That is the oversimplification, as you have said. The apple example is completely naive example. We are considering each apple as an objective, in the decision space solution as the solution of the problem. Apples are itself solutions, right? So when we are using an objective function, we can expect that that particular function is returning these values. Even you can write separate functions for separate columns.
So importance is
I have assigned importance to convert that particular problem into a single objective problem. Importance is not required for multi-objective optimization. Okay?
inside the function there is no role for importance.
No.
No multiplication.
No, but when you are avoiding that term, importance term, you will get multiple solutions. That is the problem. So I am coming to that point. Is it clear or it needs more explanation? Okay, thank you. Okay, I guess these topics are clear to you. So, in car example, as we have discussed earlier, suppose our goal is contradictory. For example, we want to reduce our cost and we want to increase the speed, right? Okay, tell me one thing. In this example, what is your decision space? Again, it is something like your Apple example. Here, the decision space is cars. Try to understand that. How to identify those cars? You can put an alphabet number, I don't care. In this case, decision space is car. You are trying to search a car, right? And those cost, speed, and those things, comfort, and whatever maybe the properties you are trying to optimize, those things are objectives. We are getting maybe confused in this point. Right? Is it clear? See, if we reduce the cost, we shall have to compromise with the speed. Right? So I am not going to pronounce this front, paradoxical front. Let me define it first. So this is an ideal situation. This is, can you tell me, is this a decision space or objective space? What do you think? It is an objective space, right? So, suppose we have two functions, f1 and f2. I am not bothering about the decision space. How many variables are there? I am not interested right now. So, why this is an ideal situation? Can you tell me? See, when we are trying to minimize this f1, and minimize this f2, we are getting a single solution. That is why it is an ideal case. As I have told you earlier, in most of the practical or real-time multi-objective problems, we cannot get a single solution. Right? Let me understand. Let us understand this point from this figure. See, let us consider a single point here. For example, this point, right? This one. So, can you tell me whether this point is better than this point or not? Just take these 2 points. Okay? So, can you tell me whether this point is better than this one or not?
No, it cannot be.
It's not possible to define, because see, here this point is lower than this point, right? In y-axis. So, it is in this dimension it is better.
Yes.
But this point is better in this dimension. Right? But compared to this point, just look at this. Compared to this point or this point, what is happening? This particular point is lower than this one, as well as in both directions it is lower, right? So we have to understand these terminologies. I want to build up a vocabulary so that you can understand the further concepts. So we have to understand dominance, efficiency, and Pareto optimality. So this is the meaning of perfection. I have said in the initial slides, I will explain what is the meaning of a perfect solution. So this is the meaning of a perfect solution, when we are getting a single solution for multi-objective problems. Okay, it is very important. A solution is non-inferior if there exists no other feasible solution with better performance with respect to any objective without having a worse performance for at least one other objective. What does it mean? Again, a solution is non-inferior if there exists no other feasible solution with better performance with respect to any objective without having a worse performance at least one other objective. It means that when you are considering a particular solution, for example, suppose this solution, okay. So this particular solution compared to this solution, if we consider, see, this particular solution is worse in both directions, isn't it? See, it is higher than this one, as well as it is standing right side of this point, so it is higher in this dimension also.
So here, dominance in terms of the dominance.
Sorry?
So
No, I have not yet defined the term dominance. I just want to introduce the concept of inferiority and non-inferiority. So these two persons, Edgeworth and Wilfredo Pareto, are the pioneers in this domain who have worked in the field of economics, and they have invented the concept of Pareto optimality. So let us understand. This is the definition of domination. What does it say? See, for all I that belongs to I to k, if IB should be less than equal to FIA. What does this mean? See, if A and B are the two solutions, then FIA cannot be inferior to this point. What we are trying to define? We are trying to define when a particular solution A is dominating another solution B. Again, we are trying to define when a particular solution A is dominating another solution B. Okay? So, here, actually we are considering it as a maximization problem. I should remember you. This is a maximization problem we are considering, and is this greater than equal to or less than equal to sign is indicating inferiority, not value-based greater or less than. Okay? So, FIA should not be inferior to B. It can be equal to B, but should not be inferior, and at least in one objective it is better. Please try to understand this definition. This is the heart of multi-objective optimization, the idea of dominance. Again, suppose we have two solutions. One solution is not in different objectives. Suppose we have n number of objectives. So suppose one solution A is not inferior to the another solution in n minus 1 dimensions, but better at least one dimension. That is called dominance. For example, let me show you the example in that plot. Let us take any example. For example, these 2 points. Okay? These 2 points are not dominating each other. Why? Because this is better in one dimension and this is better in another dimension. But for this point, see, this point is dominated by all these points, right? Are you convinced? See, just make sure that the definition is clear. We are trying to understand what is the meaning of domination.
And in the right side, the
Yeah.
we are getting a balance between F1 and F2. But here, if we are looking for F1, we are following F2.
Which point, sir?
The ideal
In the ideal situation?
If we are looking for the maximization of one, we have actually minimization of one.
Yeah.
We are using the other factor for the other.
This case?
Yes.
No, actually in this case the problem is, see, this is the ideal solution first of all. Second thing is, see, these points are non-dominating points. Why? Because all these points are lying above it, right? So these points are not dominated by any of these points. Are you getting it? So as per the definition of dominance, when a point is being dominated by other point, when that particular point is worse in all dimension, at least worse or equal, but at least worse in one dimension. At least a single dimension should be worse compared to the other solutions.
Then all the points in the F1 axis.
F1 axis, I mean on this straight line, right? Yeah.
So the rightmost point,
Rightmost point, this point. Yeah.
is dominated by his previous point.
Dominated by this point.
Yes.
Actually, in this case, what is happening? See, here the domination relationship is not shown, unfortunately, but what is happening? See, this particular point is worse in this dimension, right? This particular point is worse in this dimension, and in this case, in this scenario, these are equal, right? So this particular point is being dominated by this particular point.
So similarly in
Yeah.
this, if one feature is
Here what is happening, see, in this case, these points are non-dominated because here this is better, in one dimension it is better. But in this case, for example, this point is higher than this point, right? So this particular point is dominated by this particular point because it is in one direction smaller and one direction it is worse compared to this one, right? That's got the definition of dominance. Am I clear to all of you? You can please ask questions if you are having any doubts.
So if in this graph, real situation, one have mentioned that the middle 2 points.
Maybe.
and the,
This point
No, in this
On the card.
on the card.
on the card, okay.
On the
Yeah,
card,
these 2 points.
They also have a better for particular feature. Maybe point
Yeah,
one.
this particular point is better in compared to this one in F1 direction,
Different direction.
and this particular point is better in F2 direction. So these two are non-dominating because one is better in one direction.
So for that, we have to consider at least one to compare the dominance. At least one feature to compare the dominance.
No, not always. You can get the dominated points. In this case, these points are non-dominated. Not always every point should dominate other.
Sir, actually the thing is the change. If I check the slope, like F2 by F1, slope of the graph, like change of F2 in respect of change of F1.
Yeah.
Then when the slope is changing, so it is like for the non-linearity. So in the second graph, it is generally our all multi-objective functions are non-linear.
Typically, non-convex.
Yes. So basically, when we consider this non-linearity, so for each of space, like when we try to optimize both, because we are not keeping constant any of this function. because the function is varying itself.
Constraints can be there.
So yeah, so based on this flow, the actually the points are getting multiple because we can multiple intersection based on these slopes, right? So that's why we can generate the because slope is changed. So why can we consider the dominance?
Sir,
It is not
in the ideal situation we have a single solution.
In ideal situation, we have a single solution.
And in this case there is no single solution.
No, there is no
That
single
is the
solution.
difference. Right?
Yeah. We cannot say one solution is better.
The left hand side is intersection point. That is the solution in case of ideals.
Yeah.
Only one solution exists.
Only one solution
But
exists.
here all the points on the line has to be
Actually, for this particular graph, I am not saying. Actually, I have not checked it. Is it a parallel front or not? But in case of typical outcomes, this kind of curves will show give you the parallel front.
So the ideal case is generally it's a linear graph because the
Ideal case never happened in real. It's very rare. So you will get multiple solutions. So how we are getting multiple solutions as per the definition of dominance, right? So this is the definition. You may maybe recheck this definition or rethink about it. And if you have any doubts, you can please ask me. Again, this less than equal to and less than signs are indicating that one solution is better than other, not greater. Okay. So that depends on the problem type, whether you are and the objective type, whether you are maximizing or minimizing. It is actually indicating that if R1A is greater than this or equal or in at least one dimension, it is better. We are to all of you.
Yes, so one more thing, like if we consider the multiple objectives here, like if I try to solve every objective separately, if I want to like optimize each of the objectives separately, then it is not sure because the total object, the total function will be optimized in a proper way. So it is not
No, what happens? Again, the same issue. When you are trying to optimize one objective separately, it will give you a single solution, no issues. Whenever you are trying to solve another objective, it may and it will definitely give you another solution.
But
if it is independent then
except for the case of the ideal solution.
Yeah, except for the case of
for the ideal one, it is an independent space, right? For the each of objective, that's the independent space I have allocated for them.
Ideal situation is actually very hypothetical. It never happens. I have not found any situation that is as ideal as that graph.
So when you are comparing like this, so this point is minimum in both. But here you are not able to get such points. Because, for example, this point is doing this instance. But again, this point is again doing this such. But what's in that? This point is doing this respect. But this point is doing this. So because the curve like this, so here you are not getting single solution. Here you are getting
So all the single solutions, they do they need to be ideal?
Sorry?
Not like that.
Sorry?
If it returns a single solution, then it is required to be ideal solution.
When it is returning a single solution,
Single, only one solution.
a multi-objective problem. Yeah, if one solution exists in its Pareto front, that will not be cannot be called as a Pareto front, then it will be an ideal
So
situation.
in parallel, it has to be some competition.
Yeah, Pareto, in case of Pareto front, when we are generating the Pareto front, the definition of Pareto front is the set of the solutions, those are non-dominated.
So ideally you should try to avoid the Pareto form, although it is
Ideally, we should.
so although it becomes a Pareto form, but ideally you should try to avoid to get a single one.
No, actually,
So if we have our objective defined in a proper way, then we can get single solution.
very difficult. I have not found any single point in any real life problems in my career. So when
I think that is the reason linear programming problems are linear programming are all like planar surfaces.
yeah,
Like
LPP problems.
so the terminal point, the corners that you have are points like those ideal solutions.
Yeah, those ideal solutions. But again, if you are trying to solve any real life problems, then it is very difficult to get. If you are getting, you are lucky, but it is not I have not seen any such problem yet. So, again, the definition of non-dominated set among a set of solutions P, the non-dominated set of solutions P prime are those that are not dominated by any solution in the set P. Right? This particular set is called Pareto front or the Pareto optimal set.
So sir, one thing, like if I draw the correlation among those points, so it will be closely clustered, right?
We have some correlation.
Yes.
Yeah.
It will be closely clustered. That doesn't.
On which one? Pareto set.
For the Pareto. Because if I remove one particular attribute, then all other attributes should be missing. One attribute should be there in such a way that will handle the exact correlation of all the distributions.
In decision space.
In the decision
Yeah, but maybe there are some redundant attributes may present. You have to check the variance for that. Actually, this statement is oversimplified. We may not remove in that way. There are some standard methods like DCA or all those things. You can check it, the variance. So, may be possible to remove some attributes.
Actually, one objective is to get rid of the cluster itself. So that as small as the cluster is, the greater is the solution space.
Small as the cluster is.
As small as the cluster is, the greater is the solution.
In this case,
In the Pareto system.
Actually, when you are getting a small cluster means if that front is very small, then your decision making process will be easier. Suppose if you are having lesser options, your multi-objective method is computing some lesser points for you that indicates that you can easily choose from those points. But if you are having a large set of non-dominated set, then decision making process will be difficult.
But that is coming from the input space. I mean, the option that will come from the input space. But here we are not talking about the input space. It is simply solution space. Option means that is.
Yeah, ultimate return will be the decision variable value.
But when we are talking about the Pareto graph, then we are not directly talking about the options.
No.
When we see
Pareto front is plotted in the objective space.
Yes. So how the input space can directly manipulate or influence that Pareto?
Okay, so what is happening actually, Sir is asking an important question. Let me clarify it. I don't know whether all of you have got that point. So what is Sir trying to ask? Suppose we have a function f1, x and y. Okay, so we have two decision variables, one function. Let us consider another function f2. Sir is saying that when we are plotting f1 and f2, we are getting some Pareto fronts, right? That can be of any shape. Sir is saying what is the relation between then the relation of this Pareto front with the decision space. So let me start with the single objective function. Suppose we have only one function, we do not have this f2, then what will happen? Suppose we are trying to maximize. Okay, we are trying to maximize both of them. So suppose we have single function f1 and we are trying to maximize it. Okay?
I think sir, minimize is better. Maximize is
No problem, no issues. Let me minimize it. Okay? Now what is happening? Suppose we have only single function, then what we will get? Suppose x and y are defined, maybe from 0 to 10, y is from maybe 15 to 50. Doesn't matter. These are the ranges of the decision variable, and minimization means we have a definition of this function, and from that function we are putting some values from these ranges, and we are getting a particular value. We have to check whether that value is minimum or not, right? Suppose we got a minimum value, for example, maybe 0 point something, or maybe any value, you can consider any value. For example, this is the minimum value. So this is the outcome of your objective function, right? Agreed? Now, is it our ultimate goal? Our ultimate goal is to get the value of x and y for which we are getting this value, right? Similar case happens, then what does it mean? If you are using a single objective function, you will get two values as output. the value of x and value of y for which this f1 is minimum. Am I clear? Okay. Now, what happens in case of multi-objective optimization? We have to optimize these two functions parallel. Then it may happen, it will generate something like this, something like that Pareto front, right? As we have seen in the graph. Now, what does it mean? This Pareto front contains some outcomes, right, from F1 and F2. For each outcome, we will get corresponding values of x and y. So we have here, suppose if we have 5 outcomes in the, the 5 points in the Pareto front, then point 1, point 2, point 3, point 4, point 5, then for each points we will get value of x and y, right? So in case of multi-objective optimization, we will get a matrix that contains the point from the decision space that will give you the Pareto front in objective space. Am I clear? Okay. So I guess Pareto optimality is clear, the concept of Pareto optimality. So let us consider this function. These two are maximization functions. So we have plotted some of the values, solutions. So see here 1, 2, 3, 4 and 5. So we have drawn these lines to understand the dominance. If you have any doubts, if you just check out this definition, I have put the definition in this slide also so that you can correlate these two things simultaneously. So please check this slide. If you have any confusion, please let me know. This is the Pareto optimal front containing 1, 2, 3, 4. Why 5 is dominant by all other solutions? If it is not clear to you, please let me know. See, this particular point is dominated by these things, although it is not dominated by point number 1. Okay? But when you are considering, this is a very common confusion, that is why I put this graph. When you are computing the Pareto front, it is not necessary to find out which point is not dominated by a certain point. We have to find out those points, those are non-dominated. Those are non-dominated by all other points. Pareto front gives you the points, those are not dominated by all other points. This particular point is dominated by some points, right? That is why we are not considering this one. But these points are not dominated by any other points. Is it clear to you?
Which is not, say, point 2.
Point 2, okay? Let us discuss about point 2. So what is point 2? See, if we consider point 1 and point 2, see point 2, these two functions are maximization. So point 2 is better in F1 direction and point 1 is better in F2 direction. So these two points are not dominated. Again, check point 2 and 3. See, point 2 is better in F2 direction. Again, not dominated. If we check point 2 with point 2 is better in F2 direction and it is better in F1 direction. Again, not dominated.
But point 4.
Yeah, point 4.
It is based in the F1.
It is based in F1 but not based in F2.
So not.
See, for all other points, this particular point,
So point 1 and point 4.
Point 1 and point 4. See, point 1 is better in F2 direction and point 4 is better in F1 direction. So these two points are not dominated by each other.
So they are the solutions. Is it?
They are the Pareto front. Yeah, they are the solutions.
But 2, 3 are not solutions.
2, 3 also solutions. Those are also not dominated.
Yes.
Solutions are those points. Those points are not dominated by any other point.
2 and 3
Yeah.
are neither based in F1 or F2. Are neither based in F1 or F2. But F1
Point 2 is better.
No.
F2.
Again, see, point 2. We have a confusion here. See, if we consider point 2, we have to check this point with all other points. Okay, whether any point dominating it or not. See, point 2 is better than F1 in this direction. Okay, Point 2 is better than 3 in this direction, point 2 is better than 4 in this direction, and point 2 is better than 5 in both directions. That means it is not dominated by
No
any.
other point is greater than point F1. If no other point is greater than point 4.
Point 4, okay, in F1 direction.
F1 and no other point is greater than point 1 in F2 direction.
F2 direction.
So they are something different. They are different from the points 2 and 3.
Yeah, I got your point. Actually, that is the point said by Mr. Sen. What he was saying, he was trying to optimize each of the functions individually. If you are trying to optimize each of the functions individually, then F1 will give you 0.4, F2 will give you 0.1. But when we are combining those two functions as a multi-objective problem, you cannot say 0.4 and 0.1 are the solutions, because these are also non-dominating solutions. That is why the concept of non-dominance has been introduced.
If that would have been the solution, then you need not to optimize also.
Yeah, we need not multi-objective optimization. We will get these two solutions individually.
Yes.
There is no need to consider the multi-objective approach. Okay, so these are some other non-domination examples. You can look at it.
I have one question.
Yeah, please.
The car that has been plotted there.
That car.
Yeah.
This car.
So, is that just for highlighting all these points, or that curve also do have some significance?
No, this curve is used to highlight the Pareto front.
It has no other significance other than I have only 1, 2, 3, 4.
For discrete optimization problem, we will have that 1, 2, 3, 4 points only.
That's it.
For continuous optimization problem, we may have a continuous curve.
Actually, it is for display only because we do not know the x1, x2.
Yeah, if the range as I have described here, suppose we have discrete points for x1 and x and y, then we will get some discrete points only. But if we consider this range as a continuous one, then we will get continuous outcome in the objective space. Okay, so this is the algorithm to find the non-dominated set. So I am not going to describe all these things, and it may not be required for you. So there are some important observations. The concept of Pareto optimality and the definition that we have discussed is not required for ideal situation, as I have discussed earlier. And non-dominated set concept is applicable when there is a trade-off in solutions. So, for example, here F1 is maximized, F2 is minimization problem, and there is a trade-off between the solutions. It is not that trade-off means conflicting solutions. I am trying to say that trade-off means when two solutions are non-dominated as per definition. Okay? Trade-off doesn't mean that one objective has to be maximization, another objective has to be minimization. It can be both maximization, both minimization. Okay, let's take this example. It's a very famous example. The image is very famous. So F1 and F2, we have two functions. When F1 is minimization and F2 is minimization, this is the Pareto front we are getting. Okay? It's very interesting. Let me show you some other examples. Suppose F1 is minimization and F2 is maximization, then we are getting these Pareto fronts. These are generated in MATLAB. So,
Is it possible to represent it as an ellipse? Because
sorry, ellipse?
Yes.
I don't get you. But what you are trying to do?
In the lower ends of the ellipse, can we consider it the minimization of two functions? This area.
Yeah.
So this is the ellipse, right? So this, when I cover this area only, then F1 and F2 we can take it as a minimization of both.
Actually, I am not getting your point. I am
Ellipse
sorry.
means the blue area.
Yes.
No, that is actually the solution.
This particular area.
That is random.
This particular area.
There is the lower end, the lower half.
No, you cannot say that in that way. You have to compute the non-dominance relationship of points. This is the objective space. Shape of the objective space you cannot visualize. If it is higher dimensional objective space, you cannot visualize it. So we have to compare each solution with each other solutions to get the non-dominance or the Pareto optimal set. Without getting Pareto optimal set, you cannot draw this line. Okay.
So in some cases, maybe the Pareto-optimal line will also not be visualized. I mean, you cannot visualize the Pareto.
If it is more than 3 dimensional, it is not possible.
Maybe even then it is possible to create some surface.
If we can plot the objective space, we can visualize the pattern.
So usually in a marketing presentation, when they will plot they will not plot the inside. Suppose they are showing some examples of the car. They will always push them on the Pareto form. They will never do certain things those are inside the.
Yeah.
Because those are no help.
Yeah, definitely. Those solutions are, I mean, we cannot consider those solutions for our problem. Yeah, those solutions nobody will try to buy because those are not good for value for money. So, is it clear to all of you? We will get different Pareto fronts from the same objective space depending on the minimization and maximization problem. Okay? So here is another example you can easily visualize from this slide. When something is minimizing and we are maximizing another thing or minimizing another thing, you can easily see these Pareto fronts better compared to these curves. So if you have any confusion till now, you can please ask me. Is it clear to all of you, I guess? Okay. So, I don't know whether it's visible or not. There is another example of Pareto front, Pareto solutions. It may look like this. And all other solutions are dominated solutions. So, our goal in case of multi-objective decision making is to get this Pareto front. Okay? Our research literature have multiple types of solutions. Like, I guess all of you have heard about NSGA2. I don't know whether all of you have heard about it or not. It is a very popular paper. In fact, I have given some examples, or in the hands-on session you shall also get some example from that particular algorithm. Have you heard about it? The algorithm name is familiar to you? NSGA2? NSGA. Non-nominated sorting genetic algorithm 2. It has been published in 2002, if I am not wrong, by Dr. Kolanmoy at IIT Kanpur, Kangal Laboratory. I don't know if you have heard about it or not. This is the most cited paper in the IEEE transactions on evolutionary computation. Still now, I guess it is having more than 42,000 citations and various works have been done using that particular algorithm. So this is a very popular algorithm, although that algorithm is almost 24 years of age and many modifications have been proposed. So still, as that algorithm is very popular, I am considering examples from that algorithm in this particular presentation. So, so let me know. As I have said, the full form of NSGA is non-dominated sorting genetic algorithm. So, do you have any exposure on genetic algorithm? I mean, I am pronouncing a term, but I don't know whether all of you are getting it or not. Have you any exposure of genetic algorithms? Okay, can you please elaborate something on it? Any of you?
Finding the local minima or maxima.
Yeah.
Okay, so getting this local minima or maxima by not getting minima or maxima, we can find it continuously and checking that if we got the value, then we have to by mutation we can find the best result after some time.
Yeah.
Not finding for evolution.
Yeah, sir, exactly. You're absolutely correct. And when should we go for these algorithms? I mean, when we should go for genetic? Huh?
Or non-complex function.
Yeah. Okay. Should I?
Actually,
Huh?
when it is not known, what are the condition space is not known.
Yeah.
Everything is available as a genotype. And what properties of that is actually contributing to the objective is not known. It is getting selected or evaluated based on some objective, but it is not known. That's why there is a mixing of those is allowed.
Yes, exactly. You are absolutely right. So, from the rest of the audience, should I explain this concept or should I proceed with these slides? Actually, I have not put genetic algorithm in my slides. So,
Explain the concept.
okay, so let me explain it very briefly because the stipulated time constraint. So, we can basically divide problems in two categories, right? One can be solvable, that we can solve by some algorithm. Another one is non-solvable, right? So, non-solvable problems are very interesting research topics. We can research on it, but we are currently interested on the problems that can be solved. Now, the problems that can be solved, that means we have some algorithms for that. We can write some code and we can solve it by using some machine. So, solvable problems can be divided into two ways. One is called tractable problems. Another one is called intractable problems. Right? So, tractable problems are those problems. Those are having complexity of order of n, polynomial complexity, order of n square and so on, order of log n, log n, etc. And intractable problems are maybe order of n factorial, e to the power 2 to the power n and so on. Okay. So the problem is, as I have said you in the very beginning, that if you are dealing with some problems with such complexity, when the input space is rising, or if you are giving a value to, you are giving a lot of value in the input space, then the problem is, the computational time will be very, very high. You cannot get a solution, although you have the algorithm, but you cannot get a solution within a stipulated amount of time. Okay? That is the problem. To address that problem, what we have two typical approach. One is called heuristics, another one is meta-heuristics. So what is the meaning of heuristic? Heuristic means some intuition-based solution. For example, all of we know about greedy approach, right? Have you heard about greedy approach? I guess. So greedy is a heuristic approach. We always pick the best one in our search in journey. And what if there is no guidelines? We are using some intuition without any mathematical or formal proof. That is called heuristic. What is meta-heuristic? We are using some guiding principle. Okay, we are using some natural or maybe artificial principles to guide the overall process to get the best solution. In this process, genetic algorithm is a benchmark algorithm which was proposed by John Holland. If I am not wrong, it was in 1985. The paper was published. I cannot recall the year. As far as I remember, it was 1985. John Holland proposed this particular algorithm. What does it work? How does it work? It is inspired from our natural biological behaviors. For example, for example, a child of any human being carries some properties of their parents, like eye color, heights, right, hair color, etc. So in this case, what is happening? What was the problem? We have a huge solution space. Suppose, for example, we have 1 lakh solutions to be evaluated. We cannot evaluate such amount of solutions in stipulated amount of time. So we are trying to find out a good solution from that particular decision space or search space in a particular time span, right? In a stipulated point of time. So in GA, every solutions is typically mapped as a chromosome. Right? Suppose we have a solution X, decision variable X, and we have 0 to 10. Right? We can use this particular space as a chromosome. I mean, each solution can be mapped as a chromosome. For example, if you want to plot, if you want to get 7, we can use this particular chromosome. Okay? And the length of the chromosome can be variable. You can increase the length as per your choice. For example, suppose here we have 6 bits, right? This is called binary encoding. We have 6 bits, so we have to do 6 number of combinations, but the range is 10. How to restrict it? We can use any normalization method, like min-max normalization, right? So this is a chromosome where each value is considered as a gene. Now, how it is working? At the very beginning, we have some set of solutions that is called initial pool of solution, or initial population. Okay, so among 1 lakh solutions, suppose we have randomly chosen 100 solutions. Okay, so we have 100 chromosomes like this. Alright, now among these 100 chromosomes, we have to evaluate each of them individually. How to evaluate? We have to use that cost function or objective function. We have to put this value, we have to put the value of x inside that function, and we will get some objective value, suppose value 1, value 2, up to value 100. Right? So out of 1 lakh solutions, we have evaluated only 100 solutions till now. Now, among these 100 solutions, we have to perform selection, natural selection. Theory of natural selection we have all studied in our school days. So same thing applies here. We have to select some solutions from here. So how can we select that? One popular method is binary tournament. So what does it mean? We can randomly pick 2 solutions from here. We can randomly pick 2 solutions here, check their objective function value, and we can take the best one. Are you getting it? So we are randomly taking a particular solution or 2 particular solutions from this solution pool, and we are checking the value of the objective function, and we are taking the best one. Okay? In this way, we have to iterate 100 times to get 100 solutions. Now you may wonder, one solution may repeat several times, right? It may happen. One solution is repeating multiple times. So after selection, what we are getting? We are getting again 100 solutions, maybe with repetitions. Okay? Now, that particular pool, this is the initial population. From initial population, we are getting a pool called mating pool. Okay? We are getting a pool called mating pool. Mating pool, M-A-T-I-N-G, mating pool. So, from that particular pool, what we are doing, we are performing crossover operations. How can I do that? There are lots of methods for crossover operation. For example, let me show you. Suppose we have 2 genes. Suppose we have 2 chromosomes. Okay. Now, what is the meaning of crossover? We are exchanging information between those 2 chromosomes. Okay. For example, we have divided those chromosomes into halves, and we are exchanging a certain part. For example, this part is swapped. Okay. Then we will get 2 new chromosomes. Right? This is how genetic diversity has been introduced, and the concept of child or offspring has been introduced in this method.
Is there a practical example of this? So like what a car is? Cars can be model something genotypes.
Cars, actually individual cars are your chromosomes. Yeah. For the car example.
So then we will be picking up cars that does not exist at all.
Does not?
Features of the cars are the genes.
Features of the
cars and the chains.
features of the car. I mean, if you want to optimize price or comfort, those are the objective function. Again, that confusion. If you are trying to optimize objective like price, telematics, your car stereo and so on, those are the objectives. If you are trying to map that problem here, then each car is your solution. You are searching among cars. How to represent those cars, that's a different issue.
The question is how to represent.
Yeah, the question is how to represent that car in particular in this kind of approaches. What may be the solution? You can, suppose you have 1 lakh cars, then how to represent it? You can code it by numbers. Again, as I have told you earlier, suppose car number 1, car number 2, car number 3, and you have to design that particular objective function intelligently. So that, suppose you are getting the price of the car. How are you getting? You are getting it from a database. No function is required. Right? So put that particular number of the car and get that value.
How does that number actually map to the feature space?
Not feature space.
Not the
To identify a car.
No. So how that number is actually
Decision space.
matching to the objective space. If I select that number,
Yeah.
then I have to know how to select that number.
How to select the number? No, you don't need to know how to select the number. You can randomly number 1 lakh cars by your own. This algorithm will give you the result which car is
So
optimal.
1 lakh is for say some number.
Yeah, it was some number. Okay.
So that say 10 bits number. So 10 bits the set of numbers are there. So what are you doing?
10 bits numbers. Okay, suppose we have 10 bit number. Actually, 10 bit will not be sufficient for 1 lakh cars. So suppose we have 10 bit numbers. So if you have 1 lakh cars, you will take 100 of them randomly. You can select 100 numbers randomly. You can encode it in binary, and you will get the chromosomes.
So then how can I mutate among those cars? Because
Coming to that point, you are considering cars. So we have 100 cars. We have 100 random numbers, you have encoded it in binary, and we have written it like that. Okay? Now, suppose we are trying to optimize the price. In genetic algorithm, we cannot optimize multi-objective. Okay? Multiple objectives cannot be optimized. We can optimize only single objective. Okay? For multiple objectives, we have NSCA. So, suppose this function is giving you the price of the car. How can you get that? You can give that binary value. Suppose we have a car number 00001, something like that. You can convert this number to decimal. You can check some table or database. Just pick up the value. Okay? Is it clear? So that value will be your V1. Alright? Now we have 100 cars. We have 100 values. Alright? Next is we are selecting 2 chromosomes randomly from this initial pool of population, and we are checking these values. For cars, we are trying to minimize it. I mean minimizing the cost. Any questions, please?
So actually there is no basis of say so you are picking some so you say that some number you give and some price it will come out. Does that say hash table or something?
Hash table or something kind of.
So each of these criteria are like hash table.
Each of these criteria, when you are going for multi-objective optimization, you have to refer some table. Otherwise, how can you get the price or the other features? There is no function, no mathematical function for this. For many real-life problems, we have mathematical functions. You are actually getting confused between the table and function. For this particular price case or any other case, suppose quality of apple case, how can you get that quality value? I have
Hash
to
table is the appropriate function in this case.
this function will fetch this record from your table or database. For this example, we have to take this approach. Otherwise, how can you get that price?
sir, one process, if you need to determine the fitness score, that can be dependable. Like one, you need to check like the mileage, if it is good, giving a good mileage or cheaper price, or it is
No, when I am discussing GA, I again repeat, when I am discussing about GA is dealing with only single objective. It cannot optimize multiple objectives. That is why NSCA is there. right? To understand that concept, we are understanding this concept. Okay. So we have these values. Okay. Now we are taking some random two chromosomes. We are taking those two values, and if the a particular value is minimum compared to the other, we are just taking that value into the mating pool. So we can iterate 100 times, and we can take 100 values. Alright. So in mating pool, we are performing crossover. This is called single point crossover. We are choosing a point, and any side of that point are being swapped. So we are getting two new chromosomes, and these two chromosomes are called offsprings. Okay, like our child.
So in mating pool, should we consider only the good chromosomes?
No, we have to pick up randomly. This is a randomized process. That is why it cannot guarantee you the optimal solution or the reaching. In fact, in case of multi-objective problems, we may not always reach to the optimal parallelopron. For example, in this case, see, the dotted line is the optimal parallelopron, but we are unable to reach there. But then what is the point of using it? To save time. Okay? In most of the cases, most of the meta-heuristics give you a near optimal or optimal result. So this is the mating pool. Now, every time crossover doesn't happen, we have a term called crossover probability. Depending on that probability, we perform this crossover. Okay. Now, after performing the crossover, so if we have 100 chromosomes, we have to repeat this process 50 times, because each time we are getting two chromosomes. Right? Now, after crossover, we are getting 100 chromosomes again, right? Then, for each chromosome, we have to check the mutation probability. Mutation is another genetic operator that introduces diversity in your pool. So how to mutate? One simple mutation strategy is bit flip mutation. You can randomly check or randomly take any bit in a chromosome and you can just flip it. It will generate a new chromosome. Okay? So what steps we have followed? We have prepared an initial pool of population. We have performed selection. We have performed crossover. We have performed mutation. These three steps, when completed, we will get again 100 chromosomes.
So the bits should be injected, that should be at the center.
That was bit swap chromosome.
Yeah.
You can take any random two bits also swap
The
that.
sequence should be hampered. If I check the traveling salesman problem.
Sorry?
Traveling salesman problem.
Okay, yeah, in case of traveling salesman problem, there is another, actually the scenario is different, because in case of traveling salesman problem, we have this kind of chromosomes.
So encoding is there, no? That's
Encoding is different. You have to perform different crossover operations. For example, suppose this is a sequence and suppose this is a sequence.
Partial matrix.
Now, if we swap randomly, suppose we are swapping some part, it may happen that two B's occur here. Then you have to rectify that chromosome.
so in this case we have to do a proper encoding of the card numbers.
Not only numbers, we may have to rectify the chromosomes after the genetic operations. We actually rectify those chromosomes which are invalid.
We are assigning six. Card number 1 is having a genotype like this.
Yeah.
So that is based on some encoding of this data. It is not a random type.
Encoding, this particular type of encoding is called binary encoding. We are using it intentionally because to have these genes. If you use real encoding, that is also a type of encoding that is used for different problems. So there are different types of encoding strategy. Suppose we have used that particular binary tournament. You can use ternary tournament. There is rank-based selection, rounded field selection, and so on. So I'm not going to that much depth. It is not required here. So these particular steps, when we have completed, then we will get again 100 chromosomes, right? This set of operations, when completed, we can say one generation has been completed. Okay, this is one generation. So again, after this mutation, we will get some pool of solutions, right? That is not identical to the initial population, but we shall get again 100 solutions. Now, suppose if you write a code that will iterate for 200 times, okay? Can you please tell me how many times we have checked or evaluated the solutions in a particular generation, how many solutions have been evaluated?
Sorry, can you please repeat this?
Can we identify how many solutions we have evaluated in a particular generation?
So that is itself a parameter.
Simple.
How many are we picking up?
These solutions have been evaluated. 100 solutions only before selection. Isn't it? We have evaluated only these solutions. Evaluation means we are getting the value of the objective function. Are you getting it? We have evaluated only single time. Then we have checked with these values. We have not evaluated any solution. So we have 100 solution evaluation in the first generation, and in 200 generation we will have 200 into 100 times evaluation, right? So we will get, I guess, 20,000.
No, so we are not selecting. If you have to select few, then you have to evaluate all. No, then only we can.
No, we are selecting randomly.
Oh, random selection.
Yeah, initial pool is constructed by random selection from the original decision space. Suppose we have 1 lakh solutions, we are picking up randomly 100 solutions. Then this crossover mutation operation is introducing genetic diversity that will produce new solutions, those have not been selected yet. Okay, so this will iterate for 20,000. I'm sorry, the number of evaluation will be 20,000. So out of 1 lakh solution, if we can get a near optimal solution after running 20,000, after evaluating 20,000 solutions, it will be a good trade-off, I guess.
So actually, the objective is not to get the same solution again and again. That's why you are making the mutation.
Yeah, the mutation and crossover operations are introduced to get the genetic diversity to generate different
But
solutions.
sometimes it may be good to get the same solution to know whether. Oh no, that is never an objective. So
No, actually one thing, you are right in one sense, because suppose it may happen in one generation you got a very good solution, and due to crossover and mutation you have lost that solution. It may happen. To protect from that instance or incident, we can use a concept called elitism. It is a very simple concept where we preserve the best solution of every generation and we copy that solution directly to the next generation. That feature is called elitism.
Even we can compare the base solution
Yeah.
of each, like in first generation, when we get the base solution, until we get better than
Yeah.
previous.
Yes, exactly.
then we can preserve that.
Exactly. Elitism actually says that thing. We have to copy the best solution of every generation to the next next generation as
So
it is.
in each iteration, basically this comparison is going to happen.
Yeah. We have to preserve that solution for comparison purposes, and yes, we have to copy that
you
solution.
need certain number of elements and then forget the remaining all. Is that?
Sorry?
So from a pool, you are selecting something, some say 100, that you are saying 100 or suppose there are say 1 lakhs, from that 100 has been fixed.
Yeah.
The remaining remaining ones, is 1 lakh minus 1. So those will be
Discarded at the first place. Those solutions are discarded at the first place. But after performing those genetic operations and crossover and mutation, many of the solutions from that discarded pool will be incorporated in your present pool. I mean, clear? You're getting that point? Suppose we have 2 chromosomes. Whenever we are performing crossover operation, we are getting 2 new offsprings.
First of all, you select the 100.
100, then we are we are performing selection on that, then we are performing crossover. So when we are performing crossover, some informations are being exchanged between the chromosomes. So that will
What will be the matrix for the next generation?
after mutation we are getting the 100 solutions again, right? 100 set of solutions. So then we again perform evaluation on that solution pool. We perform selection. Then after selection, the pool is called mating level.
No, that 1 lakh solution that we started, those are gone at the first place you were saying.
Those are what means, the 99,900 solutions are discarded at the first place. But some of the solutions from that space will be incorporated after crossover and integration. Some new solutions will arrive when you are exchanging information.
Those will arrive only from the 100 ones that was started.
No, those will arrive from the rest of the solutions also. How? For example, suppose we have these two chromosomes. These two are the chromosomes, okay? Now, if we perform crossover operation, what will happen? Suppose we are extending these two parts. So 1 0 1 0 0 1 0 1, and in the bottom we can write 1 0 1 0, right? These two solutions may not be in your initial.
But the parents are also one.
Parents are gone. We will copy these two solutions in our new pool that will be.
So they are replacing the parents. They are replacing
These two are parents. They are representing parents now.
They are replacing. Parents are replacing those two.
Yeah.
From 2 we are getting 4. From 2 we are getting 4. But the parents
From 2 we are getting 4 actually, but we shall consider these two only, offsprings only.
So then it is 100 only. It's not increasing.
No, population size will not increase, but there are variations of genetic algorithm where variable population size are also allowed. Genetic algorithms actually it is a saturated field. Many researches have been performed. So variable in population is also a possible approach in GA. Okay, we shall get back to these points after the lunch break.
Yes, so that's right.
So please interrupt me actually.